Professor Radhashmi today. Sir is going to talk to us on the state of remedial germline editing. We also have two eminent personalities with us as chairpersons today, Dr. Rajvi and Dr. Kritika. So I would initially introduce Dr. Rajvi and Dr. Kritika to you. So Dr. Rajvi is a consultant in Trivector Biomed LLP and Cooper Surgicals, India. Madam has been working in the field of IVF for over 3 decades. Madam is a convener for IFS SIG on holistic medicine. Madam is an executive member of the Academy of Clinical Embryologists. Madam is also a recipient of Champion of ISAR and President Commendation Award in ISAR. Welcome you, ma'am. And the other chairperson with us today is our president of IFREF, Dr. Kritika Devi. Madam did her MBBS from Madras Medical College and MD from JIPMER. Madam did her fellowship in reproductive medicine and andrology under Professor Pandian and Dr. Radha Pandian. She underwent training program in reproductive medicine at Gleneagles Hospital, Singapore, and she is currently a consultant in Nova IVF, Fertility, Chennai. And she is also an executive committee member in IFS, Tamil Nadu chapter. Madam has presented many research papers and published a lot of research articles. Welcome you, ma'am. I request Dr. Rajvi to introduce the speaker.
Thank you, Dr. Puvitra. And it is indeed an honor and a pleasure for me to introduce the speaker for today. He is none other than Dr. Elliot Dashi. He's the former Dean of Medicine and Biological Sciences at Brown University. He is an academic physician executive. He's a graduate of the Tel Aviv University School of Medicine and the Harvard T.H. Chan School of Public Health Program in Healthcare Management. He is a former president of the Society for Reproductive Endocrinologists, the Society for Gynecological Investigations, and the American Gynecological and Obstetrical Society. He has held faculty positions in the University of Maryland, the University of Utah, and Brown University, where he is currently positioned. He's the founder and leader of the Ovarian Cancer Program of the Huntsman Cancer Research Institute, an elected member of the National Academy of Medical Science and the National Academy of Sciences. He has served on consensus committees of anti-progesterones, understanding premature birth, human embryonic stem cell research, and women's health research. He served as a co-chair of the consensus committee of reducing childbirth mortality. And he is an author and co-author of over 500 peer-reviewed publications and 120 book chapters, the editor and co-editor of 16 books. His work that he has done in this field of reproductive medicine is astonishing. And I take it as a great honor for me to have this opportunity to introduce him. And over to you, sir, for your talk on the state of remedial germline editing. A very, very exciting topic. And over to you, sir.
Well, thank you very much. I really appreciate this kind introduction, and I appreciate the opportunity to address your society. The topic, you could argue, is somewhat futuristic. It's certainly not applicable today, but I predict that it will be with us before too long, although several obstacles would have to be overcome between now and then. At the core of this story, of course, is the CRISPR-Cas9 endonuclease, which, when you stop and think about it, has been with us for less than a decade. The leading paper that reported its existence in Science magazine dates back to 2012. Of course, since that time, innumerable scientific articles and presentations and conferences and forums and the like took place. In a word, CRISPR became a dominant feature of contemporary scientific and medical life. And at one point, before too long, the prediction is it will affect our discipline and will likely be integrated into the field of IVF. The search for endonucleases has been on since the 1980s, but when it was all said and done, it was really CRISPR-Cas9 that stood out in terms of its targetability, its fidelity, its malleability, and its versatility. One can use CRISPR in the context of double-strand break or DSB-dependent editing, which is mostly going to be used for the repair of multi-base mutations. And that will, of course, result in homology-directed repair, which will provide us with the desired outcome and the correction of a mutation. Unfortunately, when you conduct double-strand break dependent editing, it also triggers non-HDR DNA repair mechanisms, that is to say, an endogenous cellular mechanism known as non-homology end joining, which gives rise to small stochastic on and off target insertions and deletions, also referred to as indels for short, and to large on-target deletions and complex rearrangements, some of which I will come back to later. A more refined and perhaps more precise way of editing would be the double-strand break independent variety of editing, which would allow us to repair only single base mutations, but hopefully with less in the way of genetic turmoil. This is accomplished by means of base editors, a family of which exists today, which essentially permits us to replace or edit every one of the existing DNA bases. For example, you could convert a CG pair to a TA counterpart or an AT pair to a GC counterpart rather selectively and specifically. This has been a major breakthrough contributed by investigators from the Broad Institute in Boston. Using these tools to edit the human germline is, of course, only one of many applications of CRISPR, and perhaps one of the more futuristic ones. But as I indicated at the beginning, the likelihood is that at some point in the reasonably near future, we may be in a position to proceed once the technology is fully worked out and safety is assured. We would be well within our right to inquire what is the objective of germline editing. And the objective would, of course, be to prevent disabling and life-truncating monogenic maladies. This is why we prefer to refer to this technology as remedial germline editing rather than as heritable human genome editing, which is the more conventional way of referring to this technology. In a way, we are proposing to replace chance with choice, which is, needless to say, a lofty goal, which seeks, in principle, to rid humanity of what some have dubbed the monogenic scourge. In other words, the multitude of heritable genetic disorders that afflict newborns, which are hard to fix in vivo postpartum or once the baby was born, but could in principle be corrected at the level of the embryo and thereby prevented outright. You might ask yourself, what is the universe of monogenic disorders that we are making reference to? And that universe is broader than you might think, in that there exist over 10,000 human monogenic disorders in the so-called OMIM database, the online Mendelian inheritance in men database, which was established and is still maintained by the Johns Hopkins Medical School. It is very much the standard of the industry. It is the database to which new entities are added, and it is the database which every pediatric geneticist, for example, would search when he or she is in need of information on a particular monogenic disorder. Edit-suitable maladies, of course, in the initial going, will probably include those for which peri and postnatal medical therapy is infeasible, those for which peri and postnatal somatic editing is ineffective, those wherein PGD is inutile, or where PGD gives rise to a rate-limited embryo complement, and we simply don't have enough embryos to work with to find an affected one that would be subjected to remedial germline editing. The target allele that in the future will likely be the subject of remedial germline editing is likely going to be a highly penetrant one, so that we have clarity on the outcome. It will probably be singular to begin with a simple task, if you will, and it has to be CRISPR accessible, which is not always the case. So those would be the requirements, and those are likely to be the conditions that would lend themselves most favorably to germline editing. Next, we could ask ourselves, what is the state of the art? And one would have to say, nascent. We are not quite ready to apply this technology for reasons which I will, of course, elaborate on, which leads to a circumstance wherein we have a technology that seems so near, and yet it is still so far. The story of germline editing, I would say, begins on April the 18th of 2015 on the pages of Protein Cell, a paper titled CRISPR-Cas9 mediated gene editing in human tripronuclear zygotes, that is to say, non-viable zygotes, that were edited by Professor Junzhou Huang from Sun Yat-sen University in China. The results of that effort, which was targeted at the wild-type beta globin gene, revealed low editing efficiency, minimal editing specificity, and limited editing uniformity, as you might expect from a very early effort, only 3 years after the initial description of CRISPR. Clearly, lots of work needed to be done. Nevertheless, by dint of this work being a first and arriving early, Nature in 2015 chose to incorporate this work into its 10 most important paper selections, what they refer to as Nature's 10, which was announced at the end of that calendar year. There were other studies of a similar nature, which I will not detail, but which really did not add much to our collective insights. On February the 3rd, 2017, a committee of the National Academy of Medicine released a report titled Human Genome Editing, Science, Ethics, and Governance. At that point, the leading recommendation was to permit clinical research trials only for early purposes of treating and preventing serious disease, and only if there is a stringent oversight system able to limit users to specified criteria. This was perhaps the first learned foray into this field, and it clearly indicated a measure of caution and a clear indication of the fact that the field was not ready for application at that time. In many ways, this was a moot gesture because in the United States, at least, heritable human genome editing is not permitted by law at this time. On August the 21st of 2017, I would say the first heavy-duty paper saw press on the matter of germline editing, a paper that was contributed by Professor Shukrat Mitalipov from the Oregon Health and Science University. The paper, which was published in Nature, attempted to correct a gene mutation that involved a disease you likely are familiar with. It's an autosomal dominant malady known as familial hypertrophic cardiomyopathy, wherein the gene responsible is the sarcomere gene, and which gives rise to what is an incurable disease up to this point, a disease that is to a degree amenable to symptomatic care, but many a times concludes with sudden cardiac death. Dr. Mitalipov undertook two different approaches to editing the human zygotes or embryos that he worked with. In the first approach, he edited the gene in question in zygotes early on, that is to say 18 hours post-fertilization, showing an editing efficiency of 67%, a mosaicism rate of 24%, meaning that not all cells were uniformly edited, which is of course unacceptable and in the future would have to be addressed. He then proceeded to edit zygotes earlier, that is to say, at the time of fertilization, which increased the editing efficiency to 72% and decreased the mosaicism rate to 2.4%. In both cases, though, he noted on-target indels, which is to say, deletions and other mutations that, again, in a clinical context, would be unacceptable. He appropriately concluded that zygotic editing at fertilization enhances editing efficiency and uniformity, if not specificity, and that further optimization will be required if clinical application is to be entertained. Interestingly, this paper was a subject of significant critique as early as August of 2018, all published on the pages of Nature. Questions were raised as to whether or not the interhomolog repair, which was proposed by Dr. Mitalipov, that presumption, does it hold up? Have the CRISPR-mediated rearrangements, large deletions, and loss of heterozygosity been missed? In other words, did he present an optimistic view, a more optimistic view than was warranted because he missed a number of shortcomings? And has the hoped for wild-type homozygosity been unequivocally documented? All of those, in all likelihood, were valid, as you will see from subsequent work that I will address in just a second. In September of 2020, a joint commission of the Royal Society and the National Academy of Medicine released, if you will, a very practical report relative to heritable human genome editing. The recommendations made included, first, no attempt should be made to establish a pregnancy from a human embryo that has undergone genome editing, that clinical use of heritable human genome editing should proceed incrementally, that clinical use of heritable human genome editing should be limited to serious monogenic diseases, and that clinical use of heritable human genome editing must guarantee impeccable editing efficiency, specificity, and uniformity, as well as euploidy and appropriate embryonic development. In December of 2020, the group of Professor Egli from Columbia University published a paper on the editing of human embryos on the pages of Cell and reported that they have noted unrepaired double-strand breaks that persist through embryonic mitosis and result in frequent chromosome loss, outright chromosome loss. In other words, the editing left the embryo short of a chromosome. They also noted off-target effects of Cas9 causing inserts, deletions, and again, chromosome loss. That gives one a sense of how early in the process we are, in the sense that the consequences of editing are quite profound and not obviously anywhere near specific enough. These findings were echoed by Professor Kathy Nayakan from the Crick Institute in London, who published on the pages of the Proceedings of the National Academy of Science a paper titled Frequent Loss of Heterozygosity in CRISPR-Cas9 Edited Early Human Embryos. She commented that further basic research is required to assess the safety of genome editing techniques in human embryo. So in summary then, embryo-based, clinically reliable, heritable human genome editing or germline editing is unlikely in the foreseeable future. It is possible that gamete-based rather than embryo-based, gamete-based heritable human genome editing using cultured stem cell-derived eggs or sperm may before too long prove to be the preferred route forward for a variety of technical reasons, mostly the fact that these cells are in culture that we have an unlimited number of those, and that we can more readily establish appropriate colonies of cells that meet all the requirements and do not suffer all the shortcomings we have brought up today. So that more or less brings us to where we are today. In other words, to a point in our collective evolution wherein the means of effecting germline editing are available, but the technology and the details thereof remain to be worked out. And so, while nobody can place a precise timeline on when these difficulties will be overcome and when and if this technology will be applied in the clinic, I think it is important that yourself and ourselves keep ourselves apprised of the progress in the field, because in my estimation, at least, it's just a question of time. In other words, I can see clearly the incorporation of this practice into our discipline at an appropriate time, the timeline being at this point uncertain. With that, I will conclude, and subject to interest, I will be happy to answer, of course, any and all questions. Thank you very much.
Thank you very much, sir. It was a wonderful presentation. It was quite enlightening for us. I request Dr. Rajvi and Dr. Kritika to please take over. Dr. Rajvi, please, discussion, please.
Thank you, Professor Adashi, for a very realistic picture of germline editing. As much as it sounds exciting, you have highlighted the limitations, although you seem very optimistic that things should be, it's a question of time. But with the extensive number of, with especially the last two papers earlier this year and in December, talk about so many more mutations. So while trying to correct one monogenic disorder, are we landing up with much more complications? How do we think that we would be able to overcome this in the near future?
Well, I would say one obvious approach would be to switch to so-called base editors, which we mentioned earlier, which do not require that the double-stranded DNA molecule be separated or broken, which is probably at the root of many of the issues that were described. That would limit perhaps the range of diseases that we can target, because there would have to be single gene mutations. But it would be a good and I think a commendable way to start, provided, I should add, of course, that base editing is shown to be safe and efficacious. There is no guarantee that that will be the case, but it strikes me as a better place to start because it is less prone to these various complications that transpire when you break the double-stranded DNA unit. So in my mind, perhaps the next generation of papers may focus on just that and may just be in a position to get us to a point where the technology is sufficiently safe and efficacious for us to embrace it. Again, I'm not suggesting that this will happen in the very near future. I'd like to hope it will happen in the lifetime of the younger member of the audience, to be sure. And And that is really all one can say today until more information becomes available. I think the very import of the subject requires that we persist, requires that we don't give up, require that we find technological solutions. And I don't have to remind this audience that when the human mind is applied to a problem in a concerted fashion, sooner or later, a solution is found. Just consider the mRNA vaccines that have been developed in record time, would not have been imaginable only 6 months earlier, and yet now are routine, if you will, and doubtlessly will serve us going forward for all kinds of maladies in a way that could not have been predicted. And I think more or less, it's that type of human progress that will sooner or later be applied to germline editing. Obviously, it doesn't have the urgency, if you will, of the COVID pandemic. But once we find the necessary time and resources to proceed along these lines, sooner or later, I am convinced, or as convinced as one can be, that a solution will be found.
Thank you, Dr. Adashi. Dr. Kritika, over to you.
Yes.
Any questions? Yeah.
Yeah. Professor, we are really enlightened, and it's such a challenging topic. You have put it beautifully in a nutshell for anyone to understand who even don't have much knowledge in this field. So first thing is, I would like to understand, what are the major diseases? What do you feel would benefit from this? Any particular diseases that you feel will definitely in future probably benefit from this gene editing? And the second doubt that I have is, although you say gamete-based genome editing is much easier and maybe accepted in many countries, but won't embryo-based editing will give us a better outcome compared to gamete-based genome editing?
Well, both are good questions, very good questions, and I'll try to do justice to both. I mentioned, of course, one entity that Dr. Mitalipov chose to pursue, and it was a single gene, so a monogenic disease that clearly had significant impact on many families around the world. The number of such entities is substantial and can be found, as I said, in the OMIM database. But I will digress for a moment and say that the OMIM database, which was created by Viktor Mirkusik, a well-known pioneering geneticist almost 30, perhaps 40 years ago, has not moved with the times in terms of developing its searchable capabilities, which brings us to another project that we are involved with, anticipating the question that you just raised, which is intended using natural language technology to convert the current OMIM database to a state whereby searches will be relatively easy and straightforward and will substantially improve the database utility. If we are successful, this will be a major success because it will essentially convert what is now a difficult database to use to one that is user-friendly and likely will be adopted by every practitioner of the art. So I would say which entities exactly, will have to be sorted out as we go, and the selection or the repertoire can and will be found, hopefully, in a improved and simplified OMIM databases. So I think that does address your first question. Your
Yes,
second
Professor,
question. Yes,
sorry
what-
to interrupt. Can you please close your slide share so we can have a good view of your...
Yeah, I'll do it. I'll do it.
Okay, thank you.
yeah, that would be safer.
Yeah, okay.
I'm not a
Okay,
I'm
it's
not
done.
a certified Zoom practitioner.
It's fine, sir. You can go on. It's done.
Remind me of your second question. I got so deep into the first one, I forgot the second.
so regarding gamete genome editing versus embryo
right.
genome editing.
Yeah. So again, we're looking into the future. We do not have at this time in vitro derived human gametes that are derived from induced pluripotent stem cells. Those of you who may have picked up an issue of Science magazine from last month, October, you will have seen a major review that Science chose to publish on the generation of gametes, human gametes, from stem cells, induced pluripotent stem cells, which could begin from skin cells, for example. Technology that is just as stunning as the one we just described. The two authors being Professor Mitinori Saito from Kyoto and Professor Katsuhiko Hayashi, both leaders in that field, which I also predict will come to maturity in our lifetime. The process has already been fully accomplished in the rodent, meaning we can now create rodent eggs and rodent pups, beginning with induced pluripotent stem cells. In the human, we have taken it as far as oogonia. We haven't gone past that yet, and that needs to be figured out. But every indication is that this will happen. It will revolutionize IVF. It will convert it from an in vivo to an in vitro procedure. It will change everything. In the United States, we are so convinced of that the National Academy of Medicine has already agreed to initially put up a workshop in 2022 on this very subject, and will likely follow that with a consensus report in 2022 or 2023, we'll see. But the feeling is that before you know it, the field will be broken either by the New York Times or by Science magazine, when and if, most likely those Japanese investigators complete the picture. So then what you have is an unlimited supply of human gametes in a dish. And if you have multiple replicates, you can perfect your technology. If you only have 8 or 10 embryos, you don't have much to work with. And you can't subject a family that is seeking a correction of a genetic disorder to, to leave them essentially hanging, because you can only work with 8 or 10 embryos at a time that are available in the course of a single cycle. So this will change everything in that you'll have an unlimited supply of gametes, all of them presumably affected, and you can in culture do far better quality work in terms of identifying those clones that are worth pulling out because they are healthy, ready to be united with the opposite gamete, create an embryo, transfer the embryo, and go from there. Again, this calls for some imagination today. And the purpose of courses like this, I think, is to open the mind to possibilities, not just to our day-to-day technological or other challenges that we face. And I think when you think about germline editing, you cannot separate it, in my mind, from in vitro gametogenesis for the foreseeable future. I could be wrong, of course, and the technology could be improved in such a way that editing embryos will become safe and efficient. But given everything I shared with you today, it's a little difficult to see at this time, which is why alternatives need to be considered. Only time will tell. But scientific progress continues. And I think you can certainly assume that for the in vitro gametogenesis field, and in all likelihood, some of that will translate into germline genome editing.
Thank you, Professor. Thank you. You have really thrown an insight into this topic. Thank you.
I am Radha Pandian, Professor Adashi. Such a wonderful and pragmatic lecture you delivered. Thank you so much. While there is enough caution among all the scientific bodies to adopt a prudent pathway, as Jennifer Doudna put it, for germline editing, how do you think we can prevent indirect this biohackers? And you heard about the report of a premature adaptation to birth of twins for HIV recessive genes and all that. So how can we prevent this biohackers and others from prematurely adopting this and then affecting the germline technique before there is a formal approval for that regarding the safety issues? How can we do that?
Right. If I understood you correctly, you were inquiring about the governance of this technology and the avoidance of premature and unsafe application thereof. And that is, of course, a difficult issue. As I mentioned, in the United States, and I will not comment on the wisdom of the law in question, but in the United States, the issue has been addressed by the passage of a law by Congress that prohibits human embryo editing. And as I said, whether that's the best approach or not, I think is a point that's worthy of debate. But the reality is that if one were to edit an embryo in the United States, one would be in principle legally liable and in principle pay the price. What happens though in an interconnected globe that we all live in, there is much going on in the way of so-called medical tourism. I'll remind you of an incident that concerned mitochondrial replacement therapy, which is also prohibited in the United States. But a practitioner from New York elected to perform the procedure in Mexico, wherein that technology ostensibly was not prohibited. And there are many examples of so-called medical tourism, whereby sometimes legitimate, at other times rogue practitioners will choose to take patients to other nations wherein the laws are either non-existent or not as strict. And preventing that is very difficult because then you get into the international arena of governance and law, which at this point is not a workable arena, meaning there is no effective international organization that can enforce its will on each and every country. Each and every country has to arrive at that decision on its own, in keeping with its history, in keeping with its religion, in keeping with its traditions, and what fits one country does not fit another. And so I think the whole issue of international governance, which has been the subject of significant attention, I might add, and a significant number of papers, really has not been resolved as a practical matter. Everybody recognizes the importance of the question that you raised, but so far there have been no concrete solutions, let alone implemented solutions. The latest foray, or the latest salvo in this area, was a report of the World Health Organization that was issued just a few months ago, wherein a major piece of the deliberation was the international governance of heritable human genome editing. Various recommendations were made, but as I mentioned earlier, enforcement is a different story. So will I be surprised if I hear that a rogue practitioner proceeded to take a patient from country A to country B and perform heritable human genome editing, and then find out, as we did in China, that the children born not only have not seen their genetic defect corrected, but perhaps have incurred new genetic ailments as a result of ineffective and, in hindsight, irresponsible editing. No, I won't be surprised. As I said, we've had precedents of that. At this time, there is no mechanism that would preclude it. Perhaps the only recommendation one can make is that every nation would be well advised to examine its preferences as to how to manage this entity. I'm not suggesting that every nation should follow the American advice, which was rather short-sighted and guided by arguments that are not necessarily transferable to other nations. So this should really be a nation-specific decision. And I only can say that, and so have others, that it would be wise, for example, in your country, to begin a process of deliberation that is ultimately brought to a head and becomes the law of the land. That will be the only way to regulate matters inside a given nation. It will still not preclude the notion of medical tourism, but the more nations adopt appropriate regulations, the less likely medical tourism will become.
Okay, thank you.
Thank you very much, sir. Thank you very much, Radha ma'am, for initiating the discussion. I request Professor Pandian to say a few words.
Professor Eli, it was a wonderful perspective. Thank you very much. I have a few points to be discussed with you. Is there a right time at all? Is there going to be a right time for gene editing? Every time we start, anything new is going to have a lot of repercussions, a lot of reservations, a lot of problems. This is what happened with the transplant. This is what happened with Bob Edwards. Luckily, the IVF baby was all right, the first baby. If it had been abnormal, it would have been back the whole thing by several decades. So somebody has to start somewhere. If you put a moratorium on this issue, and it's going to be a maverick who does it. And if instead of that, if we allow it in recognized institutions, for example, let's say with DODNA as being a guiding force, and they do it in some place, then it will be a lot better to monitor and see what's happening than to say, no, there's no, it's not allowed now in US, it's not allowed in UK. So that's what HFEA does now. It allows mitochondrial transfer in selective institution on a case-by-case basis. I think that's the way forward than to say we are not ready for it yet. We are never going to be ready. The initial days are going to be difficult for any new technique. Therefore, I think we should allow it with caveats saying that in selected institution based on criteria decided by a panel. What's your opinion on that?
I could not agree more. I mean, the last thing we want to do is hold up progress. Every field has its own issues. Fortunately, mitochondrial replacement therapy has proceeded responsibly, and so far without transfers of embryos, at least not in the UK that we know of, or in the United States, where I said it is forbidden. I think there are some pregnancies from mitochondrial replacement that are done mostly with IVF success in mind, not so much with mitochondrial DNA disease, but that's a separate story. But regrettably, this field of heritable human genome editing was severely injured by the irresponsible actions of a Chinese practitioner who really whose actions reverberated worldwide and gave the procedure a bad name and put a damper on all of it for some time to come. I'm in a way glad that commissions that have come to fruition since then, while taking into account the lessons learned from China, have not been paralyzed by it, but have taken the approach that, yes, we need to proceed, but we need to proceed with care. And I think that's what you're saying.
Yeah.
And I think that's what the field needs. It will be a shame not to proceed, not to try and perfect this technology, and not prevent the human misery that is inherent in monogenic diseases. Now that we are at least on the precipice of possibly addressing this issue. So I hope that reason will prevail and that emotion will be placed more in the background, and that we will thoughtfully think through the benefits of this approach without losing sight of the import of proceeding with the utmost caution.
Yeah, I quite agree with you. I think ethical decisions should not be based on emotions alone. It should be based on both intellect and emotions. And in fact, Dodna goes on record saying that until she saw the suffering of the patients, she was for not allowing this technique at all. Now
That's correct.
Yeah.
Yeah. No, you're right. She had a change of heart.
Yes.
And that's important because she is an important player. She is a Nobel Prize winner. She is the mother of this technology. I mean, it's hard to find anybody who is more prominent in this field. So yeah, she, I think, as perhaps a woman and as a mother, could readily appreciate what successful germline editing might do to people who are less fortunate.
Thank you very much. That is a wonderful time.
My pleasure.
Organizers, yes.
Thank you very much, sir. Thank you very much, Professor Adashi, for the wonderful presentation and for patiently answering all our queries. I thank Dr. Rajvi and Dr. Kritika for chairing the session. I thank Professor Pandian and Dr. Radha Pandian for the discussions and for the constant encouragement to conduct these meetings. I thank Sun Pharma Senora Division for helping us with the technical support. Though it was a holiday for them today, they still came to help us out with the technical support. Thank you very much, Sun Pharma Senora Division. Thank you, everyone. It was a wonderful meeting. We'll meet in the next CM. Thank you.
Good night, good day, and good night to all of you.
Good night. Thank you. Thank you.
Thank you very much.
Thank you, Pavitra.
Thank you very much.
Hi.
Thank you.
Hi, Rajvi.
Ma'am, Dr. Rajvi left.
Oh, she left already.
She just
She looked